and beyond. I'm being broadcast and recorded, not just to Florida. But. All right, so thank you so much, Carrie, for the introduction and for the invitation to come over here and chat with some of you all and talk to you a little about metal-mediated cycloaddition. So I am not making, I'm going to start this off with a series of disclaimers. I'm not making any claims that this is an exhaustive overview. More what I try to do is pick nice examples that kind of span several decades in the development of metal-mediated cycloaddition chemistry. Okay? And hopefully by the end we'll be able to come up with some kind of general guiding principles if you were, say, had to write a proposal and you were really excited about new metal-mediated cycloadditions. What are some of the key design principles that you would want to use? I can't catch a break today. What is this? Okay, I'm going to have to stand near my computer, I guess, so it doesn't go to sleep. There we go. Okay. So what is a cycloaddition? Hopefully everybody's involved themselves with cycloadditions in some way, shape, or form prior to today. But essentially, if we break this down, what a cycloaddition is that we're trading pi bonds for sigma, right? So what's everybody's favorite cycloaddition reaction? I'm assuming many people are coming from the organic background of things, right? What's your favorite cycloaddition? Or maybe what was the first cycloaddition you ever heard about? Diels-Alder, right? That's usually a lot of our entry points into cycloaddition chemistry. And it's a great reaction. I like it too. But there's lots of other types. And so we describe the Diels-Alder cycloaddition as a 4+2. So when you start to add different pi components, we start labeling them as M plus N plus O, essentially detailing the number of atoms that each fragment is bringing to the cycloaddition process. Okay? And so depending on who you talk to about this, there is a very important part or maybe less important designation of whether you put brackets around those numbers. Okay? And if you put pi, or I think it's implied that they're all pi components. So some would tell you that the brackets denote that it is perfectly concerted process, which I disagree with on a fundamental level, that nothing is actually ever concerted. All processes are, if it's a two-electron process, it's just two very rapid single-electron processes that follow each other. But, so I will use, essentially, you will see me use interchangeably the inclusion of brackets or leaving away of brackets. Just, again, this is one of my disclaimers at the beginning. So just to give you an idea of the topics that we're going to see today is to talk about 5-membered rings. So you may also be familiar with the Pauson-Khand reaction, another really awesome cycloaddition reaction. Formation of 6-membered rings, for example, the Diels-Alder reaction, but also 2+2+2 cycloadditions. So this is, my slides partially cut off. No, okay. This is going to be fun. You could also make 8-membered rings if you start talking about doing 4+4. And then, as Carrie alluded to, I will shamelessly plug some of my own chemistry in talking about the cycloaddition to make 4-membered rings towards the end today. So just to kind of, as a refresher and mostly to give you some literature references if you're interested in going to read more about orbital symmetry rules. This is a really important topic, so much so that it earned a Nobel Prize for some of the developers here. But really, essentially what this boils down to is based on symmetry rules alone, you can determine whether or not a cycloaddition would be thermally or photochemically allowed. Okay? And so the 4+2 Diels-Alder reaction is thermally allowed based on orbital symmetry rules because you don't have the crossing of those orbitals. But a 2+2, adding the caveat here of suprafacially, is thermally forbidden but photochemically allowed. If you do a 2+2 anterofacially, that is thermally allowed. Okay? So it's not a one-size-fits-all comment there. However, if we start thinking about using transition metals, orbital symmetry rules are beautiful and wonderful, and I like them very much. But once you introduce a transition metal, it has all these d orbitals that have very different shapes. Those rules don't really apply anymore. Okay? You're also taking a process of a thermal or even a photochemical cycloaddition and taking it from a concerted or mostly concerted process And now you're breaking that down and doing that stepwise. And so this is really one of the exciting things that can be introduced when you start using transition metals to mediate these cycloadditions. Another benefit, aside from orbital symmetry considerations that you can access when you use transition metals, is that now, what else do we know transition metals are really good at doing? Oh, they coordinate ligands. I heard this over here. Okay, it's okay to answer questions that I'm posing. They're really good at coordinating ligands. And what could be really great ligands? Pi components, right? They have these accessible electrons that can donate to a metal center. What's also great is because they have these pi orbitals, they can also be pi acceptors, which can further strengthen those metal-ligand interactions. And so when you use pi components and think about them as ligands, now you can actually lower entropic barriers because you're pre-organizing the various pi components that you want to have come together and cyclize by bringing them together using that metal as basically a templating agent there. And the other great thing about metals is they can coordinate your pi substrates, but they also have other ligands that can support them. And by modulating those ligands, you can start changing things like regio and even stereo control. There's a lot of benefits when we start using transition metals here. And so I wanted to provide you with several reviews. The reason why I'm saying that this is not going to be an exhaustive in any way, shape, or form presentation today is because there's a lot of reviews who do a much better job. And I think if you go click on some of these, you'll notice that there's literally no possible way I could cover all of this material in an hour and a half this morning. So here are some nice, really nice reviews that kind of span a lot of this chemistry. And I tried to pick things. Let me see. Yeah, everything was published since I was born, so it's not super old, but still some of it's a little old. And then just because at one point someone told me that students really like slides that have pictures of people's faces. I included the photos of a lot of the people who really are to credit to pushing forward this field. So does anybody recognize any of these people?
Volhard on the left.
Steve Volhard over there, yeah. Mark Loudens is over here. Paul Wender. I feel like this is not necessarily peak stash photo, which I don't necessarily does him credit because that's very glorious. I shouldn't say this because I'm sorry. I know Paul's not going to watch this, but I'm sorry. Does anybody know who the last person is here? That's Neil Shore. Okay, so let's dive in. So the first reaction I wanted to touch on is the Pauson-Khand reaction, partially because it's a little bit of an outlier in terms of mechanistic considerations of how this works. And also, you'll see up at the top here, I have some additional reviews if you're interested more particularly on the Pauson-Khand reaction. So we think about the Pauson-Khand reaction, there are certainly other catalysts that are able to achieve this overall 2 + 2 + 1. So this is one of the examples where one of our pi components actually just donates one atom. I should also add a caveat. You'll notice that there's no 3-membered rings. So think about cyclopropanation, azeridation, epoxidation. Technically, they would fall under trading pi for sigma bonds umbrella, but I'm not going to be including the 3-membered ring formation today. But the Pauson-Khand reaction allows us to bring alkyne, alkene, and a carbonyl together to make 5-membered rings. So this is really a really powerful reaction when you think about the products that you're getting from pretty simple starting materials, right? You're making this cyclopentenone, which now has 2 different ways it can serve as a reactive compound. So the typical catalysts that we see that are used here are usually based on cobalt and rhodium. Okay, there's certainly other catalysts that promote this reaction, but if Kiri came into lab and said, we really need to make this cyclopentenone, and you have to, for whatever reason, make it via Pauson-Khand, right? You're like, ooh, okay, I got to figure out how to make this work. You would probably reach for one of these 2 catalysts. There's other options, but they would be the first things you'd go to look for. They are the most common. I'm sure Carrie does not just barge into lab like the Kool-Aid man demand you make random things and with no explanation behind it whatsoever. And then various different promoters can be added in that essentially can increase the rate of CO dissociation, because you may notice that while certainly we need one equivalent of CO to be included in the final product there, you'll notice that these typical catalysts are often carbonyl rich. Okay? So mechanistically this does play a role and can be part of the issue in making these reactions highly efficient. And so when we think about cobalt octocarbonyl, this is not a monomeric species. It's actually a dimeric cobalt species where you have bridging COs. And so one way to think about this is that we have exchange of basically our best ligand other than carbonyl in here, and that's the alkyne. This is actually one of the key parts of the Pauson-Khand is you need a good enough pi ligand that can do one of these CO displacements. Okay? Because what do we know about carbonyl, carbon monoxide as a ligand? Is it a good one or a bad one? It's a pretty good one most of the time, right? It's a really good pi acceptor, does a lot of back bonding. So you need to have a pretty decent ligand in order for that ligand exchange to be facilitated. So essentially what happens is we have loss of two COs and coordination of that alkyne. And this is thought to proceed by this kind of bimetallic activation here. So remember that essentially I'm drawing this as if there are two metallocyclopropanes that we use. So we're using two of those pi bonds of the alkyne. But really this is just a resonant structure that's denoting the fact that this is highly activated by those cobalts. Right? So we can also think about it as this is just an alkyne that's coordinated as a pi ligand there. And then once we have this more activated species, we need to have another ligand exchange, so an alkene for a CO. And now we have the alkene coordinated. And generally we don't think about, in these systems, the degree of alkene activation, similar to alkyne activation, isn't typically as much, but this does allow a migratory insertion to occur. And so most of the time when I think about Pauson-Khand, you're thinking it's just a series of migratory insertions. What's really happening here? The key part is you need to get that alkyne, you need that first ligand to go on and be activated. Okay? So you get a migratory insertion of this alkene. A lot of the examples that we're going to see of Pauson-Khand reactions that I've pulled, one of the ways that the catalysis can be accelerated is that you connect this alkene to the alkyne, right? Anytime you bring things intramolecularly, a lot of reactions that are very challenging to occur intermolecularly can happen intra because you're basically lowered that, or you've increased that effective molarity of your second substrate. So alkene migratory insertion followed by carbonyl migratory insertion. And now this is followed. Does anybody know what this process would be called? What would we call that?
Reductive elimination.
Right. So reductive elimination. That's why we need that alkyne here to be activating that cobalt so we can be oxidized so that we can ultimately form that final carbon-carbon bond here. And now we have that cyclopentenone, and one of the reasons why you often will see a pressure of CO be used in these reactions is you're basically trying to fight the different considerations of you need CO to come off the metal at some point in order to get into the catalytic cycle, but then to release the product that you formed, that cyclopentenone, you also need COs to come back on. So there's a balance of how much CO you need to have dissolved and available at any given time. And so that allows us to release that cyclopentenone product. So let's look at some specific examples. So I know I said, okay, cobalt octocarbonyl and rhodium carbonyls, those are going to be your catalysts that allow you to do Pauson-Khand. But I wanted to show this fairly unique example of a titanium, or this titanosyne that's able to do this. Also because this is a way for this to be deemed enantioselective. You noticed previously when you just have COs. Have you ever heard of a chiral CO? And that's kind of challenging, right? It's a nice, flat, linear compound, right? So really challenging if your ligand set is achiral by nature ligands, how could you ever then make an extension of an enantioselective catalysis? So this is where this chiral titanosine pre-catalyst that developed by Buchwald was introduced that allowed this. Again, notice that the E9 component that goes into making that five-membered ring, they are tethered here. And again, 15 atmospheres of CO were required. So there's the pressure of CO that I was talking about. And so in this particular case, now we're starting with titanium, okay? Cobalt, rhodium, late transition metals. When we go to titanium, we have a slightly different mechanism here, okay? There's not as many COs, and this is by design. By using that titanosine, we're limiting the number of COs that are on that substrate. And now we don't necessarily have this bimetallic coordination and activation mode, but we still have this metallocyclopropene from the titanium be formed, and that's our initial step that activates, again, selectively the alkyne component. And now this can undergo migratory insertions to make that six-membered metallocycle, which undergoes reductive elimination to turn that process over. And so if you're interested in reading more about this, all of the references are going to be up on the screen for you. And then another example of using rhodium to do an enantioselective Pauson-Khand shown here. Again, this is an intramolecular example of that E9. Those two components are tethered together using S-BiNAp, which is obviously many of you might be familiar with BiNAp, commercially available. It's a little pricey, but not too bad. Again, now lowering the pressure of CO to only 1 atmosphere. And now you'll notice in here 12 mole% silver triflate. Should there, like, I don't know about you all, but when I read papers and I see silver anything, little alarm bells go off in my head. It's like bing, 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 bing. So if we see a catalytic amount of silver used and a rhodium-1 pre-catalyst, what should that signal to us? What's probably the role of silver?
Forming ionic rhodium.
Right. We're going to rip that chloride off to make a cationic rhodium intermediate, which generally is going to help activate it towards these processes. Okay. So anytime this is pretty common if you work with rhodium, you see a lot of silver added in there. That's often used to help activate to make that rhodiums that are more cationic, more electrophilic. And so in this particular case, of this more monomeric rhodium case, when we have BiNAp coordinated, now we have initially that coordination of the E9 substrate, and this undergoes actually an oxidative cyclization. Okay? And this forms this rhodocycle, which can then undergo migratory insertion. So this is slightly different mechanistically than we saw for the cobalt Pauson-Khand, right? There was an activation of that alkyne followed by 2 migratory insertions. Where here, we're actually getting a direct oxidative cyclization event. So you're oxidizing the metal at the same time that you're forming one of the carbon-carbon bonds that ends up in the product. Versus the cobalt case, you're activating the substrate first, and then migratory insertions are what starts forming those carbon-carbon bonds. That makes sense? Okay. And that came, this millennium, so progress has being occurred. So this is a little bit out of order from, I think, the slides that I sent to Kiri, because I realized that I put them out of order before I sent them, but I've fixed it for now. So in addition to Pauson-Khand to make 5-membered rings that are all carbon, I wanted to just highlight some more recent literature that's been developed in the area of making paroles via a formal 2+2+1. Okay? And so we can use 2 alkynes and an azobenzene compound as the source of the 1 atom here. And so in 2016, Ian Tonks at University of Minnesota developed this titanium catalyzed process that essentially the pre-catalyst that starts off, that enters the catalytic cycle, is this titanium amido. Okay, so we have this titanium amido. So does anybody know the oxidation state of this particular titanium amido? What would make sense here? There's not a lot of options for titanium, right? So this is titanium 2. Okay, so titanium 2 is ultimately what undergoes this. Am I right? Yeah, it's titanium 2. Okay, so it's titanium 2, and this actually undergoes a 2+2 cycloaddition. This is one of the really cool things about titaniums, is that they like to make ligand multiple bonds, and then they're actually pretty good about doing 2+2s. And so a lot of times we think about making carbon or organic cyclic structures. We think about making 4-membered rings. We think, oh, that's a strain. Those are not the easiest cycloadditions to do. But when you involve a metal, metals love to actually make 4-membered metallocycles. I'm sure Kiri has a lot more knowledge about metallocycle 4-membered rings than the outer edge audience member maybe. And now this titanocycle can undergo coordination of another equivalent of an alkyne, and then migratory insertion followed by reductive elimination. And that's how that parole is formed under those conditions. So here we're taking advantage of the fact that titanium is excellent at making metal ligand multiple bonds. And then even more recently, just earlier this year, along the similar lines report of a vanadium-catalyzed. I don't want to call it a variant because it is quite different. A vanadium-catalyzed parole synthesis of a formal 2+2+1 cycloaddition, again with alkynes and these azobenzenes. And now the pre-catalyst that actually starts off the 2+2 chemistry is vanadium-4 bis amido, vanadium-5 bis amido. Okay, I always get confused when I write that out because it's a V and a V. No, whatever. I didn't have coffee today, but so we have this vanadium bis amido, and then this is the active species that undergoes the 2+2 cycloaddition to make a vanadium. Vanadium cycle here, and notice that this is still supported by another amido here, and this can undergo again migratory insertion of another equivalent of alkyne followed by reductive elimination. So this is slightly different in terms of the pre-catalysts that we're supporting in these methods. So some early metals and some late metal examples of 2+2+1 cycloadditions. Okay, so we all love the Diels-Alder reaction. This is obviously a given. And so when we think about those reactions, depending on what your bearings are for high temperatures, maybe you think 135 degrees is hot, maybe you don't. But if we were to just take these two particular dienes that I'm showing here, in order to affect a 4+2 cycloaddition, to make this yield, or this compound that I've shown here, you are required to heat this to 135 degrees. Okay, so thermally allowed does not mean thermally easy, right? A lot of times we're like, oh, well, it's an allowed process, or even if something, oh, it's a spontaneous process. Yeah, so is turning coal into diamonds, right? Delta G is negative, but it doesn't tell you anything about rates. I feel like I have this conversation in my organic chemistry class often. Yes, but it doesn't tell you if it's fast or not. Delta G just says it can happen, right? Thermodynamically, you're allowed to do it. But when we do this 4+2 in this way, it requires high temperatures, and also you're kind of limited to just whatever those substrates decide their inherent reactivity is. You're kind of stuck with that reactivity. Okay? But by the inclusion of a nickel catalyst in this particular case, so please forgive my typo here, this is diethyl aluminum chloride. Right? We don't have a really magical aluminum species in here. That would be quite remarkable. So essentially the role of that aluminum is actually kind of important. We start with nickel 2. This serves as a reductant to get us to nickel 0 that allows us to enter this catalytic cycle. And when we use nickel here, now we're fundamentally changing effectively which diene serves as the diene, the 4, and which diene serves as the 2, right? So in the thermal, purely thermal example, the electron poor diene is actually serving as the diene component, okay? And then butadiene is serving as the dienophile, if we use our more generic terms. But in the presence of this nickel catalyst, we see that chemoselectivity is completely inverted. We're exclusively seeing butadiene serve as the diene component, and the electron poor diene, I think this is methyl sorbate, serve as the dienophile here. And exclusively that terminal alkene is the dienophile component there. And essentially what we're seeing here is just a mixture of diastereomers. So if we take a little bit of a look into the mechanism that's proposed for this nickel-catalyzed process and why this makes this different is that we're able to form this nickel 0 diene complex that also is able to coordinate it prefers to coordinate to the distal, that terminal alkene of the sorbate. And then this can undergo, what would we call this process? It's an important one when we're talking about cycloadditions. This is our oxidative cyclization step, okay? We can do this oxidative cyclization, which allows us to form this nickel allele. And now, from this nickel allele, it exists in equilibrium between the eta-3 and eta-1 form of that. And now, once we form, it prefers to exist and reductively eliminate from the eta-1 allele isomer. And this can undergo that reductive elimination to give that 4-member ring product eventually. So, there's not, I don't know that I would have necessarily predicted that this chemoselectivity between these two alkenes of that diene, but this is what they experimentally observed in there. Okay. And so, what if we don't want to just do a catalyzed Diels-Alder? There's also, if you, I'm sure many of you are probably aware, if you really want to do a Diels-Alder, but you don't necessarily need to go through an oxidative cyclization mechanism, what would you do if you needed to make your Diels-Alder not be at 135 degrees? Any ideas? Lewis acid, right? If you activate that dienophile, usually is the #1 strategy. You activate that dienophile, you make that much more reactive. You can not only you can lower that kinetic barrier and make that process go at much lower temperatures, but also a lot of the strategies allow you to append chiral ligands to that Lewis acid, and you can have an anti-selective Diels-Alder process too. That does mean, though, that your dienophile needs to have a Lewis base very proximal to the alkene, but there are certainly ways to do that. But if we wanted to expand upon just a more traditional Diels-Alder, if we wanted to look at an intramolecular example, this is coming from Paul Wender's group. Again, we're going to have an intramolecular example of the diene, and in this case, an alkyne. So, and please forgive the bad bond angle of this alkyne. This is more to show connectivity of atoms. I'm aware of the proper geometry of sp hybridized carbons, so I'm sorry about that. And again, you'll notice that nickel cod is the metal of choice in this example, and they're able to make this with stereoselectivity by this choice of this phosphite ligand. And this is now able to be done at room temperature, which is a really nice improvement of this to get this cyclohexadiene type product. And so what's really interesting about this particular case is they noticed there was a really distinct effect on the ratio of nickel to phosphite ligand. So at a 1-to-1 ratio, nickel to phosphite, they actually don't see the 4+2 product, right? They see this cycloisomerization occur. That's kind of interesting. At 3:1, so we have a slight excess of phosphite relative to nickel. This is the nice spot where we can selectively obtain that 4+2. And then if we push that ratio even further, well, now the reaction barely even goes. So how can we rationalize and understand these different effects? Okay, well, if we think about mechanistically a pretty reasonable pathway for this reactivity to occur, again, we would have a nickel 0 species coordinate the diene and alkyne components there. A pretty reasonable next step would be an oxidative cyclization, right? And we get to this metallocycle, again, that is going to, because we're doing an oxidative cyclization that involves a diene, we're going to have an allele, a nickel allele. So it's going to be either 801 or 803. But if we consider the two different 801 isomers of this, if we consider this particular 801, that's the product of oxidative cyclization. And now, if we want to get to if we want to complete a catalytic cycle, we simply need to have the nickel be reduced again. Okay, so if this does a reductive elimination, that's where we get that cycloisomerization product. Okay, and this is what's preferred when we have low amounts of phosphite to nickel ratios. But at higher phosphite to nickel ratios, this particular 801 nickel would be preferred, and that this is what can undergo reductive elimination to form that 4+2 product. Does this make sense? Right? How does this make sense? What we think about this is, if there's not a lot of phosphite around, what does L sub n really mean at that point? How many phosphites do you think are on that nickel? Probably one, right? And so at low ratios of phosphite to nickel, we're able to, we're acting more through this internal 801 species, likely because we can actually access this. We don't have all these other phosphites adding steric encumbrance around that metal center, so we can more freely go between all of these different forms. But when we're at higher ratios of nickel to phosphite, now the sterics around that nickel center are much more sensitive, because we probably, instead of having just one phosphite, probably two, right? It's more likely that we're going to be more saturated in that nickel regime. And so now it's going to be more sensitive to the sterics at that nickel, promoting this 801 form, which then can undergo that reductive elimination. So then, why does it make sense if you flood it with phosphite, we really just don't see anything?
You never get beneficial stuff.
If there's too many phosphites, you have too much competition for your substrate, right? I think this is one of the, this is kind of telling about this cycle, is that, well, yes, this is going to be a really nice intramolecular chelating substrate. You still have to knock off the cod, first of all. Those of you who've ever tried to make nickel 0 complexes started from nickel cod probably know some of the agony of the first cod. No problem. You can do lots of ligand substitutions to remove that first cod. The second cod, good luck. You have to have a really good ligand. It can happen, but it's on paper it's super easy. In real life, it can be very disappointing. You see your NMR and realize, okay, still have a cod complex. So I think a lot of this has to do with when we have too much phosphite, we just have too much competition for ligand exchange in order to enter that catalytic cycle that's productive. Okay?
Would the phosphite also help prevent the beta hydride elimination needed for the triene complex?
Yes, that's another component here, that if we have too much phosphite, you're never, you're prohibiting the fact that you are saturated at the nickel center, so you don't have the open coordination site for beta hydrogen elimination. Yes. Okay, so that's an important part of beta hydrogen elimination. It really needs an open coordination site. If you don't have an open coordination site, you don't get beta hydrogen elimination. In addition to alkenes and alkynes as components for 4+2 cycloadditions, what if you used an allene, right? So this is kind of ties back into when I talked about 2+2s being suprafacially allowed, but disallowed, but anterofacially allowed. If you use an allene, this allows you to break those rules, because when you think about what that accumulated carbon in the middle, what the orbitals look like in that picture. Remember that allenes have two sets of pi bonds, but they're not parallel to each other, right? They're perpendicular. So you actually have that central carbon has two sets of pi or p orbitals that are perpendicular to each other. So it's actually how you're allowed to then do anterofacial on an alkene. It's a special alkene. Okay? But in this particular case, there's a stark difference by the choice of metal. So what we've seen so far for 4+2s is a lot of nickel zero chemistry. So if you were to use basically the same pre-catalyst set that we saw previously with the alkynes, is that we use nickel, cod, and a phosphite. Again, that 3-to-1 ratio is a nice sweet spot in the middle. If you subject that to those conditions at room temperature, you do see a 4+2 occurring, but the 2 component comes from the terminal end of that allene. Okay? Notice that my shading here is a little faint on this screen, but the pink double bonds, those end up not in the 6-membered ring formed from the diene, right? But they found that if instead of using nickel, if they used a rhodium-1 pre-catalyst, again, same phosphite ligand, if they do this, now they can still achieve a 4+2, but they're using instead that internal alkene component. And I think this really just has to do with the preference of the metallocycles that are formed when you use either of these metals. Okay? So this is a nice example of just by changing the metal that you're using, you can observe different reactivities. Talk faster. Okay, so this is probably the oldest reaction that I'm going to show you today because it's a really good one. Okay, so there's not a lot of reasons for us to probably dig back through the chemistry literature from the 1940s. People were doing wonderful things back then, no shade. However, this was really the first example of a metal-mediated cycloaddition reaction. And here they're reporting, again, using a nickel zero pre-catalyst, able to do a 2+2+2 trimerization of alkynes. Okay, so this is a really nice way to make benzenes. One of the drawbacks from this can often be that the regioselectivity of the products that you get, not always super well controlled. But this is really kind of this was a monumental step forward at the time because really had not seen a lot of chemistry that allows you to do this type of reactivity. And again, probably no surprise since we've just talked about this fairly frequently, is that these reactions are believed to proceed via initially the coordination of those two alkynes, followed by an oxidative cyclization to make a nickel metallocycle. And then this can undergo ligand exchange with a third equivalent of an alkyne. Again, a migratory insertion followed by reductive elimination and replacement of those the ligands on nickel to turn this over and produce benzene is kind of what we would expect mechanistically for this to be achieved by. What was I going to mention about this? Just blanked. But you can also notice that there may not necessarily be a very high degree of selectivity simply by having these two different R groups, especially if they're not very highly significantly differentiated between each other. But this was still like really a monumental leap forward in terms of traditional metal catalysis and making benzenes. So, the other thing I wanted to mention, this is really pretty cool that you can take 3 equivalents of the same substrate and have them all come together and make a product, right? If we were to think about no metal included in here, that's wild, right? You just take a minute to think about that. You want 3 things to come together all at the exact same time and produce a product. That's like magic, essentially, right? Because think about, anytime you have any chemical reaction, you need 2 molecules to collide with each other in solution. First of all, they need to find each other. Second of all, the collision needs to be productive, right? It can always be reversible. So to ask not just 2 molecules to come together at the exact same time, to ask all 3 to come together at the exact same time, basically toss all their electrons into a blender, spin them around, and make a product, pretty amazing, right? And science doesn't really work that way, right? That's really, really difficult. And so this is really was a primary example of how using a metal allows you to pre-coordinate and essentially activate ligands prior to this reactivity. So essentially you are doing a ternary reaction, but you're doing that stepwise. This allows you to break that down and do that stepwise. So a nice example from the literature that's used in complex molecule synthesis. Really like this example because I don't know that I would look at estrone and say, oh yeah, I'm going to make that benzene ring, right? It's usually something when we try and break down complex targets. We often, I mean, maybe I just don't think about things the same way, but I don't always look at a benzene and say, I'm going to make the benzene ring there. I usually would look at this and say, I'm going to think about ways I can make the aliphatic portion, but I'm going to start with the aromatic ring and then I'm going to build from it. That's going to be one of my building blocks. But this is a really cool example where they kind of do the opposite. They have the aliphatic framework in place and then they build in that benzene ring. It's a really nice example from Peter Volhar making estrone. And I wanted to toss this in because I really like this example, and again, it comes from the more recent literature, but it kind of takes us and reminds us that you can also make heterocycles via cycloadditions as well. And so we can use this pegylated imine that's conjugated and with an external Michael acceptor. And so in this case, the alkyne component can either be a Michael acceptor or it could be a styrene derivative to make pyridines with very high regioselectivity. And again, we're seeing a pretty common culprit here in terms of a metal pre-catalyst using rhodium. And here we have 2 equivalents of silver acetate. Okay, so it's not catalytic, so it's probably not just going to be used to rip a halogen off the rhodium. So when we see catalytic amounts of silver salts, that again, bing, 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 what should that tell us? What's silver probably doing here?
It's ripping off the pegylate after.
It's a good idea.
You need to oxidize up to the purity.
Right. Here, this is going to be, when we see, typically when we see stoichiometric amounts of silver, we think about its role is going to be as an oxidant. So in this particular case, its role is as an oxidant and as an activator to make a cationic rhodium. Okay? So this is a really nice example, and then I'm sure the ACS would love me to have a disclaimer on here. This figure was taken directly from this paper and whatever their disclaimer. I just had to sign one of those publishing agreements that's like, this is your work, but it's ours now. There should be a disclaimer. I did not draw this. This is taken directly from the paper. So I'm making that very clear. But this is for educational purposes, so please don't sue me, ACS. And so we start with this rhodium CP pre-catalyst. And essentially, one of the first steps here, so maybe I should back up a second. We may think about, since what we've just been talking about, we may look at this and say, okay, well, why can't we just have everything coordinate to the rhodium, oxidative cyclization, reductive elimination, done, right? Okay, yeah, sure, maybe that sounds semi-reasonable, but it doesn't account for the fact that we still need to lose that pegylate from the nitrogen or why was the pivlate ever there, kind of. And so mechanistically, they did a lot of really nice experiments in this particular paper, if you're interested to see more what they did there. But they did some of these isotope labeling experiments where they carried this out with deuterated acetic acid, and they stopped this at partial conversion. And what they found is, not necessarily surprisingly, that they had deuterium incorporation very extensively in that 2-methyl position adjacent to that pyridine nitrogen in the product. They also saw a small amount at that 3 position, and then in their recovered starting material, they have 25% deuterium incorporation in that beta position. That's pretty interesting, right? So how can you propose a mechanism that keeps all of these considerations in mind? And so what they came up with is that initially the way we actually enter into this catalytic cycle is that there is this is probably coordination assisted here, an acetate mediated deprotonation of that beta position of that oxime ether starting material. And that's where we actually get into this cycle. And then from this point, so if we go from compound 2 to compound 3, essentially what we're doing there is we're losing acetate. So this is where we are now. We're at a cationic species rhodocycle here, and this is helpful, and probably dissociation is mediated by the fact that there's a pivlate there. So we can have this intramolecular sort of ligand-assisted dissociation of that acetate, and this allows that external alkene to come in and coordinate. And it's from this species 4 that they believe that migratory insertion can occur, and this will have this prescribed selectivity, and this is what helps control that regioselectivity. That's mostly, you can think about that, it's governed by electronic effects. You have a polarized alkene there. And now we're at species 5. So what do we need to do in order to progress more towards product? Well, we can do a deprotonation. So we go from cationic rhodium to a neutral species via deprotonation. And they're explaining the fact that they have that deuterium incorporation in that 2 position by the fact that this methyl group is deprotonated at that time in order to get to that neutral species, which then can be much faster at undergoing this. If you really want to push arrows, the way I think about this is that we're basically doing a bond migration of this rhodium carbon, migrates over. That allows us to break that weak NO bond. We form that pivlate rhodium that's now coordinated at that nitrogen of our pre-pyridine. And essentially what we need to do in order to get to products and turn our catalytic cycle over again is we need to do a deprotonation and tautomerization. And that loops us back over. And so effectively, what we're getting to now is we need to do a reductive, the reductive part of this process is actually forming pivlic acid, right? It's not actually making the organic product that we're really excited about, these pyridines that we're making. It's just an acid. And then this rhodium is why, that's formed, is why we need silver in there to be that terminal oxidant to turn this back over. Sorry, I talked too much without clicking a slide. It's my computer's way of being like, all right, wrap it up. Okay. And so this is a really nice way. And again, I mentioned too that this silver has a dual role. Actually, how we enter into this cycle to begin with is we can activate that by ripping that chloride out using a small amount of that, a catalytic amount of that silver also to enter into this cycle. So this is, I think, quite mechanistically distinct from what we've seen from a lot of these other 4+2s, of these oxidative cyclizations, reductive eliminations to make the cycles that are formed here. Okay. And then I think this is the last 2+2+2. again, forming pyridines in this way. You can also think about using as the components alkynes, but also I don't always think about nitriles as being super reactive. I think a lot of us use acetonitrile fairly commonly. You're like, oh, it won't do anything bad. It usually doesn't. Doesn't usually participate. This is a nice example where you can actually use a nitrile as one of your two components in a 2 + 2 + 2 to make pyridines. And then this was developed by Janice Louis' group using these pyridine dialdamine ligands and an iron 2 precatalyst. And this is an in situ activation method using a small amount of zinc in order to presumably do a reduction of the iron 2 to get to the active species of these kind of reactions. And so mechanistically, this is more likely to do an oxidative cyclization migratory insertion type of pathway. And I lied. That was not the last 2 + 2 + 2. I'll be quickly. This is exciting, especially because this is regioselective and diastereo and enantioselective. So this is a really nice example of this E9 substrate combined with an external alkyne rhodium-catalyzed using a phosphine-based ligand. Look what we have there. Catalytic amount of silver. Guess what it does? You're right. It rips off a halogen. It rips off that halogen to activate the rhodium catalyst. And essentially here, they're getting 10-to-1 regioselectivity, which that's very good. So this is why I'm categorizing this regioselective. And that's basically governed by that insertion step that we would expect of that alkyne external component. And I just wanted to show that they did assess a variety of bisphosphine ligands, and they found that these had some, I would categorize these all as good to excellent EEs, basically ranging from 86% EE to 97% EE. And the takeaway message that they presented in this particular paper was that more sterically bulky ligands were better at differentiating between the alkyne termini, which totally makes sense, and that's going to govern that the regioselectivity of the products. And so here we see a bulky ligand, very nice ratio between those two different regioisomers. But then they say that the better pi acidic ligands increase the EE significantly. So we're basically looking at comparing these two ligands with these two ligands, and that change in EE is a few kcals, or probably less than 2 kcals difference between those two different enantiomers of transition states. So I would like to see maybe more metrics on that, but this is the general takeaway that they had on this particular case, is that the electronics are better differentiating between the two different enantiomeric transition states, and the steric factors of the ligands is what's determining the differences in the regiochemistry of that insertion. So I think those are probably pretty good broad considerations to take away from this. I'm going to have like half an hour. Okay. I won't talk for another half an hour, I promise. I know you're like, oh, God. Okay. I remember being a student still. I did not have a very long attention span even then. So 4 + 4 cycloadditions. If you want to make 8-membered rings, okay, there's a few ways you can think about doing this. You could take butadiene and wait for that to dimerize, but one of the problems if you were to just try and do this thermally, if you took butadiene and by itself and just heated it up for a while, actually what you get is a lot of vinyl cyclohexene. Okay, one of my favorite things to kind of dig up and start feuds about is that the original Deals and Alder paper that reports 4 + 2 cycloadditions, right? You go think about this, and a lot of times the prototypical example of a 4 + 2 cycloaddition that we think about is butadiene and ethylene to make cyclohexene. Super cool reaction. totally fake. Okay? When you do that, you actually make vinyl cyclohexene. That's by far the major product because butadiene is so much more reactive than ethylene would be. Okay? Ethylene's pretty challenging in an unmetal-mediated process. But if you were to add in a nickel zero species, and this particular paper, they did not necessarily, or I could not determine what the ratio is between the cyclooctadiene and vinyl cyclohexene, but it does participate in cyclization chemistry. But if we started to electronically differentiate that diene, okay, so go to methyl sorbate again, nickel zero, and benzene allows us to do selectively a 4+4 cycloaddition, and presumably that stereochemistry of the two ester groups there is mostly just governed by thermodynamics. Prefer to be anti rather than syn product there. But if you were to think a little bit more deeply why, I still think there's probably, this is the octadiene is probably, the cyclooctadiene, probably the favored product when you just use butadiene, is that, again, we're starting with nickel zero pre-catalyst. We make a nickel-butadiene alkene complex. This can undergo oxidative cyclization. We can form carbon-carbon bonds, but there's basically 3 different variations of that intermediate that you've formed upon oxidative cyclization. So you can have an A-1, A-3, nickel allyls. Okay, this pretty clearly, I think, is the easiest way for us to see. Okay, we can go from this A-1, A-3 nickel allyl. This slips into a bis A-1 nickel allyls. This undergoes reductive elimination, and that's how we're going to get the vinyl cyclohexene product. Okay, I think everyone buys that. But when you start thinking about this bis A-3, where both of those allyls are syn, okay, with respect to the nickel, we then do, if these if we think about them as the bis A-1s of this form, now that can undergo that reductive elimination. This is one of my favorite looking molecules because it looks like a spider with tweezers. No, I'm the only one who sees this? Okay. Well, maybe you'll always see this now. But this is one of those molecules I'm like, it just looks kind of cool. Okay, and so this 1,2-divinyl cis cyclobutane would be the product of a reductive elimination from this intermediate. And now this itself can undergo a thermal 3,3 sigma-tropic rearrangement to access the cyclooctadiene. So that's actually one way to do this. But then if we start to just consider the bis A-3 anti-allyls, those can go to the corresponding terminal bis A-1 allyls, and now this would be what undergoes reductive elimination to directly access the cyclooctadiene. Okay? So kind of 2 roads lead to the same product versus the vinyl cyclohexene up there. And again, iron can be implicated in some of this chemistry. So this is really nice chemistry from the mid-'80s from Tom Deek. So that's actually his last name. His first name is not Tom. Last name is Tom Deek. Really, really beautiful chemistry that I got to learn a lot about when I was a postdoc. But what this work uncovered was that using a catalytic amount of this 1,2-diimine, we call them DI ligands, from an iron 2 catalyst in the presence of magnesium butadiene, which is actually a really cool compound if you're ever looking for a nice reducing source of butadiene. Magnesium butadiene is a nice solid if you don't want to work with butadiene gas all the time. Really, it's a very convenient reactant. But they saw that using, that kind of defeats the purpose. They're using butadiene itself here. But this was used essentially as an activator for that nickel-2 pre-catalyst. And that what they observed here is a high level of selectivity for the cyclooctadiene over that vinyl cyclohexene when they're added this diimine ligand. And then in 2016, a report by Ritter on a modification of this allowed them, essentially, the pre-catalyst that they use is a preformed cod. So they basically, it's one of those, you make cod from cod, which is kind of cool. They start with a pre-catalyst iron that's actually pre-reduced. So you're not adding an activator into that system. And this is, it's like greater than 99.99 to whatever ratio. So it's very, very selective for the production of cod in those cases. Not just nickel can do cycloaddition chemistry. And so this is when the portion of my shameless plug for myself steps in. So some of this was some of the work that I did as a postdoc in the realm of 2+2 metal-mediated cycloadditions. So I did not develop this chemistry. This came before me. This was done by Sarah Russell in Paul's lab. And she found that this bis-aminopyridine-supported iron pre-catalyst was a fairly unique example of promoting, in this particular case, an intramolecular 2+2 cycloaddition of electronically unactivated alkenes. And these ligands these pre-catalysts are really cool, or running these reactions are kind of fun because, you're not supposed to just look at colors of reactions and to tell you anything. Your eyeball is not a spectrometer that counts for anything. But these are really fun because these pre-catalysts are a really nice green color. Add in the substrate, it goes brown. And then when the reaction is done, it goes back to green. So it's a really easy way to tell, oh, it's done. These reactions would be typically very fast. I always would get a stern look when I would say remarks like this in subgroup. That doesn't count as a metric, but it was really easy to monitor things. So these were, we work in a lab a lot. I'm sure you all can commiserate that. Sometimes things aren't as exciting as other careers maybe are. So reactions changing color can be a highlight. But these are very fast catalysts. Reactions are done typically very quickly. And a lot of really nice mechanistic work, which was performed by a subsequent graduate student around the time that I was joining the group, found that the way that these proceed is that formally these iron bis-aminopyridine ligand complexes, formally it's iron 0. But spectroscopically, we know that's not the best description of them. So spectroscopically, the iron pre-catalyst that's used is actually iron 2. Okay? And the way we get to that is those imines are each singly reduced. Okay? So that's where we're getting spectroscopically iron 2, but formally still iron 0. Okay? The electrons actually are residing on the ligand rather than on the metal. But upon ligand exchange, so in solution these do coordinate one equivalent of dinitrogen, but in the presence of these alkenes, that ligand exchange allows the access of this formation of this 5-membered di-olefin complex. And now this is actually still, again, formally iron 0, but spectroscopically best described as iron 1. Okay? So essentially, we go from having a 4-coordinate iron to 5-coordinate iron. One of the electrons on that diimine ligand goes back to the iron. That's just the best configuration of where all the electrons want to sit in that complex when we're now a 5-coordinate. Now, this spectroscopically iron 1 di-olefin compound undergoes oxidative cyclization to iron 3. And now this iron 3 intermediate can undergo this reductive elimination to form the cyclobutane ring, which is somewhat unique. We didn't see a lot of examples, even though some of those complexes certainly could have done a 4-membered ring forming reductive elimination. They did not. This reductive elimination to make that cyclobutane, which arrives us back at iron 1, di-olefin compound. But it's the reason why, I'm sure you're all like, oh, this lady's crazy, talking about the colors of reactions being interesting. The reason why that's actually fairly important because that was actually a pretty early indicator to us that there was an electronic change between the resting state during catalysis and the resting state of that pre-catalyst. Okay? Because notice here, during catalysis, when we're at 5 coordinate species, we're iron 1, iron 3. But as soon as all of that substrate is used up, we actually go back to the dinitrogen complex, which is iron 2. And that's actually the colors we were seeing when you're running this reactivity. Which is cool, pretty cool, talking about, like, obviously we all know the way colors happen is you have a homo-lumo gap and light and excitation, and your eyeballs do cool biological things that let you see colors. But here we're actually seeing an electron move between atoms, and that's where you're seeing color changes. I don't know. I thought that was pretty cool. I got to work on some of this. And then the moving of this this platform into an intermolecular example work that I did when I was here, simply by learning a lot more about the resting states, about these immunopyridine complexes, by incorporating additional groups in the positions in the imine. So what I'm talking about is now notice there's ethyl groups next to those imines where previously they were methyl. It doesn't seem like a big difference, but it really does change the geometry constraints of a lot of these proposed intermediates. And this was kind of the unlocking of allowing us to do this in an intermolecular example. And this kind of goes back to a little bit we were talking about before with the nickel and the phosphite case. So if we don't have an open coordination site for beta hydroelimination, guess what? Beta hydroelimination doesn't happen. That allows reductive elimination to predominate. So we learned that when we were keeping the electronic and also the steric components of these aryl groups that I've shown in blue here, when those are fairly are small, when they are large, that actually allows us to enforce that reductive elimination to make cyclobutanes. And beta hydroelimination is suppressed because those groups also stay coordinated. So we never have one of those imines associate, which would then open up a coordination site for beta hydroelimination. We use that to our advantage a little bit later, but that's not a cycloaddition, so I'm not going to have this one here. But then also, I just want to, again, a quick plug for myself. This chemistry was not limited to just iron. This could also be done from a cobalt platform. The cobalt platform is a little bit different from the iron, mostly in that the pre-catalyst is, again, formally a cobalt-0 pre-catalyst, but spectroscopically is cobalt-1. And this was really cool because we could follow this chemistry by EPR, which is at room temperature EPR, because we had a ligand-centered radical. So if you had a cobalt-centered radical, you definitely need to be doing EPR at low temperatures. That would kind of be painful to do. But because this was actually able to be done at room temperature, because we had a ligand-centered radical, we could follow that fairly easily and see the differentiation between the pre-catalyst, which was a cobalt dinitrogen complex, which undergoes now, cobalt-1 is going to prefer, or formerly cobalt-0, but cobalt-1 is going to prefer four coordination environment, right? It's going to prefer square planar, right? So essentially what we observed here was a square planar ligand exchange, dinitrogen for an alkene complex. So in this particular case, we're actually able to observe independently the monoolefin, the bis-olefin complex, which actually undergoes a dissociation of one of those imine arms, followed by oxidative cyclization. Upon cyclization, that that second imine comes back on to coordinate, and then this is what we believe is promoting that reductive elimination, is the re-coordination of that second imine arm to allow the reductive elimination to occur in that particular case. So this is a very broad overview of things, but if we think about what are some of the common threads that we saw for a lot of these metal-mediated cycloadditions, not just about when you have a redox active ligand, right? We're talking about a lot of the examples are late transition metals that are reduced, right? So we're talking about nickel 0, D10. Okay, we're talking about cobalt 1 or 0. Okay, again, we're pretty reduced metals there. Talking about rhodium 1, right? So D8 when we go further down the periodic table. And those all generally proceeded via an oxidative cyclization and reductive elimination pathways, right? But then what happened when we go to early metals? Go to early metals. Are they reduced anymore? The active species that participated in the cycloaddition chemistry, they're all oxidized. They're all pretty fully oxidized, or not, I guess the titanium wasn't fully oxidized, right? But we have oxidized metals when you go to early transition metals, okay? So if you were going to think about developing new cycloaddition chemistries, if you want to work with early metals, probably going to have to start from an oxidized metal precursor in order to get into this chemistry. And a lot more of that chemistry relies on migratory insertions, okay? And so those are considerations you'd want to have. Or if you want to work with late transition metals, you want to be in an environment that you can undergo oxidative cyclization and reductive elimination with or without migratory insertions in between, depending on the size of rings that you're trying to form there too. Okay, so maybe I picked some examples that are more leading towards those conclusions, because those were, I think, are the bigger ideas here. But there are certainly plenty other examples of metal-mediated cycloadditions. So if you're curious, there's lots of reviews and articles at the beginning for you to take a look at. Okay. Do you guys have any questions? I know everyone's shy, and I'm not going to ask the question. I remember that.
Well, I was curious about how the iron chemistry mentioned the reactions between the fast and freeze out and characterize two sites.
So, in the cases, I think I showed, this is by far, this is the second fastest substrate that I'm showing here. The actual substrate, so notice I cheated and just put E here. The bis olefin and the metallocycles that were able to freeze out, those were actually from substrates that were not so fast.
From different substrates.
And those were skill plus fortunate cases that they were able to be isolated out. But yeah, that was, it'd be nice if all catalysis worked like that. You could actually no, we're making this. Look, see, here's a crystal structure. But those were, yeah, and it was definitely one of those cases where, why is this better isolated as a metallocycle? What is special about that group? It's not super obvious. Why is this other one isolated as the bis olefin? It's not super obvious. It was kind of a, let's try all of them and see where they sit, essentially.
With the nickel-catalyzed 4+2 that you showed earlier, did it react with the 1 alkene not? Would it always react with a more electron-rich alkene with the two?
So you're talking about
I assume it goes. Yeah.
the 4+4 that you said, the 2+2?
Yeah, the one on the. Oh no, yeah, the 4+2. You said you wouldn't be able to predict which alkene it reacts with.
Right. I don't know that I would have looked at that and said, okay, thermally, 100% that product. I actually think I would have predicted the inverse with a different regioselectivity, right? Or chemoselectivity, I guess. That would have been maybe my naive assumption of that. But that's just not what is experimentally observed.
Oh.
And then in the nickel case, I think it was, again, I cannot speak for what their intention necessarily were, but I don't know that they carried this out thinking that this was definitely the isomer product they were gonna get out of that. Because again, I think I may have still probably predicted that this alkene would have been more likely the dienophile, but I think this maybe has more to do with the fact you are going through metallocycles, and that the pushing this ester group further away from the metal when you do that reductive elimination appears at least to be more favorable. But yeah, I don't know that I would have looked at this and said, yes, obviously this will be the product that you will start with.